Hello, my name is Zach, and I am doing my presentation on graphs and pathfinding. First of all, what is a graph? A graph is a data structure used to represent connected items. This could be anything from a road map to a power system or computer network. The items in a graph are called vertices, and they are represented by the numbered circles in this illustration. The connections between them are called edges. Together, edges and vertices can be used to make up paths. Some graphs have edges that only go in one direction. This is an example of such a graph. Here you can see two directed edges and one undirected edge. Edges can also have weights applied to them. This could, for example, in a road map, indicate the distance that a certain edge takes to travel between two locations. If you want to find a specific path between two vertices, a pathfinding algorithm can be used. Pathfinding is very important to things like computer networks or GPS systems. Computer networks use pathfinding to figure out how packets should be routed through the network. GPS systems make use of pathfinding algorithms to determine which roads a traveler should take to reach their destination. Algorithms that operate over graphs need to do graph traversals, meaning they need to be able to visit the vertexes of a graph in some order. The first graph traversal algorithm we will consider is the breadth-first search. This algorithm takes starting vertex as input and outputs a full list of vertexes in the graph. The time complexity of this algorithm is O of v plus e, where v is the number of vertexes and e is the number of edges. Now let's look at how the breadth-first search would traverse this simple graph. The starting vertex is A, and thus the algorithm will visit the A vertex first. Next, it will visit all vertexes that are linked distance 1 away from A, then all vertexes distance 2 away from A, and finally all vertexes distance 3 away from A. In a larger graph, this would continue until all vertexes were listed. Notice how the edge between E and F remained black. This is because the breadth-first search will not go over any edges to vertexes that were already visited earlier in the algorithm. Alright, now let's reset the graph and take a look at more specifically how this algorithm traverses the graph. Internally, the algorithm uses three different data structures. The first is the frontier queue that represents the frontier of where the search algorithm has been. The next is a set that contains all nodes or vertices that the search algorithm has found. And the last is a pointer to the current vertex that the search algorithm is working from. Let's start the algorithm again at a search starting from vertex A. The first step of the breadth-first search is to add the starting vertex A to the frontier queue and the discovered set. Once this is completed, we can begin the main program loop. The first step of the main algorithm loop is to take the front item in the frontier queue and set it as the current vertex. Next, all undiscovered vertexes that are neighbors of the current vertex are added to the discovered set in the frontier queue. In this case, it would be vertex B and vertex D. This concludes the first iteration of the loop, and it continues with popping out the front vertex of the frontier queue and setting it as the current vertex, in this case B. Next, all neighbors of B that have not been visited are added to the discovered set and frontier queue. A is a neighbor of B, but it has already been discovered, so it won't be added to either the set or the queue. E and F, however, have not been discovered yet, so they are added to both the frontier queue and the discovered set. At this point, this iteration of the loop ends, and we continue again by setting D to the current vertex. This iteration, no new vertexes are added to either the frontier queue or the discovered set because D's only neighbor, A, has already been discovered. So we continue with the next iteration of the loop, with vertex E being set to the current vertex. Again, E's neighbors have both been discovered, so we continue to vertex F. F has a neighbor, C, that has not been discovered, so it is added to the frontier queue and the discovered set. We now continue with node C, which is at the front of the frontier queue. C has no undiscovered neighbors, so the loop terminates, and with no new element in the frontier queue to set as the current vertex, the search algorithm completes. Let's look at the whole process one more time. Again, we start by adding the starting vertex to the frontier queue and discovered set. We visit the front vertex in the frontier queue, A. We discover A's undiscovered neighbors. We visit the next item in the frontier queue, B. We discover B's undiscovered neighbors. We move on to the next item in the queue, D, and discover its undiscovered neighbors. We move on to the next item in the queue, E, and discover its undiscovered neighbors. We move on to the next item in the queue, F, and discover its undiscovered neighbors. We move on to the next item in the queue, C, and discover its undiscovered neighbors. We now have no items in the queue, so the algorithm completes, and we have a full discovered set of all vertexes in the graph. Another graph traversal algorithm is the depth-first search. Like the breadth-first search, the depth-first search takes a starting vertex as an input and outputs a full list of vertexes in the graph. It also has a time complexity of O of V plus E, where V is the number of vertexes and E is the number of edges. Let's look at how the depth-first search traverses this simple graph. Starting at node A, the depth-first search will choose one of its neighbors, and then choose one of its neighbors, and one of its neighbors, and so on until it reaches an endpoint. If the depth-first search chose vertex D first, it would immediately reach an endpoint and mark that path as visited. Next, it would backtrack to node A again, and then look at its unvisited neighbors, and go from neighbor to neighbor until it reached an endpoint, in which case it would find the path A, B, F, C. It would then backtrack to a node with unvisited neighbors, in this case F with neighbor E. It would mark that path as visited as well. We can see that the depth-first search traverses the entire graph and visits all the nodes, but the order is very different. Let's reset the graph and look again more specifically how the depth-first search algorithm works. Like the breadth-first search, it has three internal data structures: a stack, a visited set, and a current pointer to the current working vertex. The first step of the depth-first search is to add the starting node to the stack. Now we can begin the main loop. The first step of the loop is to take the end item from the stack and set it as the current vertex. The current vertex is then added to the visited set, and all of the current vertex's neighbors are added to the stack. This completes the first iteration of the loop. The loop now continues by taking the end item from the stack and setting it as the current vertex, in this case D. D is added to the visited set, and all of D's neighbors are added to the stack. This terminates the second iteration of the loop. Notice how A was added to the stack even though it's already been visited. This is because it's the main loop's responsibility to only visit nodes that have not been visited. In this case, the next iteration of the loop skips to node B being the current vertex, and no action is performed for vertex A. Again, the first step of the main loop for this iteration is to add the current vertex B to the visited set, and then all of B's neighbors are added to the stack. And this completes this iteration of the loop, and we move on to the next iteration. The next unvisited node, F, is set to the current vertex. F is added to the visited set, and all of F's neighbors are added to the stack. This completes the operation on F. Notice that E is listed in the stack twice. Once E has been visited, the second occurrence will be skipped. The next iteration of the loop sets the current vertex to E. E is added to the visited set, and all of E's neighbors are added to the stack. This completes the iteration on E. We now move to the next unvisited node in the stack, which is C, skipping B and F. C is added to the visited set, and C's neighbors are added to the stack. We now can skip through all the stack because all of the nodes have been visited. and this completes the depth-first search algorithm. Let's reset the graph and do an overview of depth-first search again. We start with our starting node A on the stack, and we enter the main loop. We take the last non-visited item from the stack and set it as the current vertex. We set the current vertex as visited, and we add all of its neighbors to the stack. We then skip to the next unvisited item in the stack, D. We add the current vertex to the visited set and its neighbors to the stack. We then skip to the next unvisited item, B. We add B to the visited set and add its neighbors to the stack. We now skip to the next unvisited item, F. We add F to the visited set and add its neighbors to the stack. We then skip to the next unvisited item, E. We add E to the visited set and add its neighbors to the stack. We now skip to the next unvisited item, C. We add C to the visited set and add its neighbors to the stack. We now skip to the next unvisited item, which there is none, which completes the depth-first search. Depth-first search and breadth-first search can both be used to find all the vertexes in a graph, but unfortunately, they both have problems. Namely, depth-first search and breadth-first search don't always find the best path. Consider this ring-shaped graph. Performing a depth-first search will traverse the vertexes in this order. If we use this algorithm to find a path, for instance from A to F, the path is much longer than it needs to be because A and F are directly connected. Performing a breadth-first search gives us better paths on this graph, but from a computer standpoint, when they only have the starting node, it's not obvious which algorithm should be used to traverse the graph. This can get even more complicated when weights are added to the edges. Here we can see that the path that breadth-first search found from A to F is length 10, while the length of the path depth-first search found is length 5. Neither of these algorithms look at weight information when they're selecting their edges, so there's no way to know if the paths they find will be actually the shortest paths. An example of an algorithm that can find the shortest paths is Dijkstra's shortest path algorithm. The input for this algorithm is a list of all vertices in the graph and a starting vertex. And the output is the shortest path from all vertices in the graph to the starting vertex. The time complexity of this algorithm depends on its implementation. If the unvisited vertices are stored in an array, the time complexity is O of V squared. If they're stored in a minimum binary heap, the time complexity is O of quantity V plus E times log of V. Looking at our simple graph again, this is the result that the Dijkstra's shortest path algorithm will find. To make this a little bit more interesting and highlight Dijkstra's strengths, let's go ahead and add weights to the edges of this graph. Dijkstra's shortest path algorithm uses two data structures. The first is an unvisited priority queue that keeps track of which vertices have not yet been visited by the algorithm, and a current vertex pointer. Now we can actually start the algorithm. And the first thing we're going to do is we're going to make all the vertexes bigger, because we're actually going to have to store a little bit more information about each vertex as the algorithm progresses. Each vertex is given a distance and predecessor pointer. The distance value is a number that represents the distance from that vertex to the starting vertex. The predecessor pointer points to the vertex. The predecessor pointer points to the previous vertex on the shortest path. Next, all vertexes are added to the unvisited priority queue, and the distance from the starting point for the starting point vertex A is set to 0. This pushes A to the top of the priority queue. The priority queue makes sure that the next vertex visited is the unvisited vertex that is closest to the starting point. We now begin the main loop of Dijkstra's algorithm. The first step of this is to take the first value from the priority queue and set it as the current vertex. Now we go through each neighbor of the current vertex and compare its current distance to an alternative distance through the current vertex. In the case of B, we can travel to the starting vertex A directly, so this vertex is updated to have a distance of 3 and a predecessor of A. Similarly, D can be updated to have a distance of 5 and a predecessor of A. We now move on to the next iteration of the loop. The next element is moved out of the priority queue, in this case B, which is currently the closest unvisited vertex to A. B's neighbors are now evaluated the same way we did with A. The first neighbor to look at is A. A path from A to A through B would have a length 6. This is more than A's current distance, 0. So this element is skipped. Next we look at E. A path from E to A has a distance of 9 when going through B, and this is better than the current distance of infinity. So we replace E's elements with this, giving E a distance 9 through B. We now look at F. A path from F to A through B has a distance 4, which is better than the current distance of infinity. So we update F. Throughout this process, the priority queue has been keeping track of which unvisited vertex is closest to A. And in that case, the next vertex we'll visit is F. We'll repeat the same process. Looking at B, a path from B to A through F would have distance 7, which is worse than the current distance of 3, so nothing is done. Looking at C, a path from C to A through F would have distance 8, and this is better than the current distance infinity, so C is updated. Next, we'll look at E. The distance from E to A through F is 6, which is better than the current distance of 9 through B, so E is updated. We now continue with the next item in the priority queue, which is D. D does not offer any paths to A through itself, so we now move on to E, which also does not provide any better paths through itself, and we look at C last. As you can see, Dijkstra's shortest path algorithm found the best path from any vertex in the graph to A. Just like depth and breadth first search, Dijkstra's shortest path visited every vertex, but it also guarantees that the paths it found are the shortest available in the graph. To do this, it took into account the weights of edges while it was doing its calculation. In review, graphs can be used to represent groups of things that are interconnected. Examples of this include roads, computer networks, or utilities such as water or electricity. Breadth first search and depth first search can be used to list all vertexes in a graph, but they have some downsides. Dijkstra's shortest path can find the best paths in a connected graph.